Hi, today I like to put an exciting circuit together called ZVS or Zero Voltage Switching driver? I don't know why they call it that. Maybe because the circuit changes state when a voltage passes zero? It doesn't matter. This is one of the simplest high-power coil drivers that can be the basis of many exciting circuits, like an induction heater that I'm gonna make today, or a super high voltage generator, or... well, one video at a time. Let's see if I can figure this one first. One search over the web and you find this circuit. The way it works is there are two transistors and oh, why did they draw it like this? Here, I drew it in a more familiar arrangement for you. Does it look familiar now? No? Fine. Here, you might be more familiar with this one. It is called an astable multi-vibrator. Vibrator? What? Just call it an astable oscillator. Just grow up, you little child! Basically, this circuit is unstable and these transistors switch on and off periodically non-stop. So you can switch things on and off with it. Here, I added two LEDs to the circuit to switch, and if I power it up... oh, and this is a battery-operated variable power supply I got to use with my breadboard. Pretty convenient. Power it up, and there, LEDs start blinking. Now I can even add a relay to the circuit and switch AC with it, like lamps. Okay, I put the lamp and circuit together, and if I plug it in, initially the lights will be off. Or on? I guess if I turn on the circuit, it... did I misconnect something? Well, yeah, the relay must be in series with the lamp, not parallel with the lamp, otherwise it will short the live wires. Isn't it obvious? Check your connections. Well, this failed, but something that hasn't failed are my Raycon Everyday E25 earbuds. Premium sound quality with tons of oomph. Well, that's bass. Super small profile, freedom from wires with 6 hours of playtime, and starting at half the price of other premium earbuds, and yet sounding as amazing, if not better. They sound so good. What are you waiting for? Click on my link in the description and get yours at 15% off. Okay, let's go back a bit. This is an N-channel Mosfet transistor. If the gate source voltage rises above a threshold, the drain source terminals that were open before will almost short circuit like a switch. Now this simple circuit is a bistable circuit, meaning that it has two stable states. Imagine we just turn the power supply on. Initially, both transistors are off and the resistor voltages rise with the supply. Even between similar components, there are minor differences. So one of these transistors turns on earlier than the other one. Say Q1 closes like a switch, pulling this voltage down, which is also the gate voltage of Q2, which keeps Q2 off. So this voltage stays high, keeping Q1 on. The circuit is stable in this state and won't change unless an external force like a switch pulls this voltage down, turning Q1 off. So now the drain of Q1 rises, turning Q2 on. Now even if I let go of the switch, the circuit is stuck in this new state. Unless I add another switch here to change the state back. I put the bistable circuit with my relays and lamps together. Let's turn it on. Oh jeez! My bar for a functioning circuit is pretty low. Let's press the switch. No, it's working. Now let's make some changes to the circuit. The drain voltage of each transistor goes through a capacitor to the gate of the other transistor, which is also connected to a resistor divider. If you're using a BJT transistor instead, you don't need these pull-down resistors because it already acts like a pull-down here. Again, when we turn on the power supply, one of these transistors turns on earlier than the other one. Say Q1, and its drain voltage drops rapidly. And we know capacitors are like short circuit against rapid voltage changes. So the voltage on this side also drops, turning Q2 off. With Q2 off, this voltage and that voltage are high, keeping Q1 on. But now this capacitor will be charging through this resistor divider, and so this voltage starts going up. This voltage will eventually rise above the threshold voltage of Q2, turning it on, and so its drain voltage will rapidly drop, and through the capacitor this voltage drops, turning Q1 off. And of course now through the resistor divider, the capacitor charges, raising the voltage here, which eventually will turn Q1 on and Q2 off. And this is an astable vibrator, oscillator, whatever. Here I simply add the relay coil between my supply and Mosfet, and if I turn it on, there you go, start switching. Simple as what happened? It seems, damn it, I killed one of my Mosfets. Here's the problem. When the transistor turns on, there is current running through the coil of the relay. And when I turn the transistor off, the inductance still wants to push the current through. So the voltage across it flips, and at this point, the voltage shoots well above the power supply level. Connected to the drain, this voltage doesn't have enough energy to kill my transistor, but the gate of the transistor is quite weak, so it can easily die. The solution is to add a diode like this across the coil, called the freewheeling diode or a flyback diode. Here I added diode across the coils and there you go. Now we are ready to add lamps and AC power. Okay, here's my circuit with the relays, and if I plug it in, okay, and the lights are off, and if I turn it on, hey, it's working! It's working! Now to the ZVS circuit. It's basically the same thing, just that there are a bunch of inductors and capacitors. L1 and C1 has a certain resonance frequency equal to this equation, and the circuit oscillates at that resonance. L2 and L3 are picked to be much larger, like over 10 times larger than L1, so they have little effect on the resonance frequency. But they filter massive AC voltage and currents from the supply voltage. And oh boy, they are massive. The way this circuit works is, imagine Q1 is on because its gate voltage is high, meaning that the LC circuit voltage is swinging up and down. On the way down though, through this diode, it pulls the gate voltage of Q1 down, turning it off. So now this voltage rises. This voltage going up raises the gate voltage of Q2 and turns it on. And so now this voltage swings up and down. And again, on the way down, through the diode, it pulls the gate voltage down, turning Q2 off, and the cycle continues. Let me show you. See, you don't need a scope and tools and components to start learning electronics. All you need is what we call a SPICE simulation program. You put your components in there and connect them up, and you can probe all the voltages and currents and learn the circuit. There are tons of different SPICE simulators out there, but like many of us engineers, I've been using this free LT SPICE software for many years now, which is quite simple and robust. After we run the simulation, if we probe here, we see there is initially this misbehaviors that are due to capacitor and these big inductors resonating that dies away. If I zoom here, you can clearly see those half sine waves on the drain of the Mosfet I was talking about. Now if we probe Q2 drain, we see the other half of the sine wave I was talking about, and the peak of the voltage is 37 volts, well above my 12 volt supply, and that's the power of resonance. And of course, because these big inductors are isolating the voltage from the power supply. And this high voltage is why we have diodes here to drive the gates. This makes sure that when the voltage here rises, the diode turns off and the gate voltage is pulled up by these pull-up resistors to the supply voltage. Mosfet gates can handle 16 to 20 volts, and because my power supply is 12 volts, I remove those Zener and pull down resistors from the gates. Otherwise, I should put them in. Now let me show you something even more magnificent. If we look at the current through the inductor, see, it is plus minus 30 amps, almost the same as the capacitor current. But the current through L2 and L3 is much smaller. If we zoom on those, they're just around plus minus 0.8 amps. And this current is mostly not coming from the power supply. As you see, they are mostly pouring it back and forth into the resonance circuit. If we look at the power supply current, so small. It's around 80 milliamp DC plus minus 200 milliamp AC, maintaining 30 amp 37 volts of resonance. And that's the power of resonance. This tiny bit of current from the power supply is necessary to overcome the resistive and radiation losses through the components. The massive 30 amp 37 volt peak oscillation mostly only creates reactive power, which is not a loss, just oscillation. Okay, I designed the circuit and ordered the parts. Let's put them together. And done. Okay, turn it on. Okay. Are you afraid? Me? No, I'm not.
Are you little?
Well, it's on. Oh, it could blow any time.
Nah, it won't.
Oh, what is that sound?
Many days later.
Well, I spent some good time improving the circuit, and now I'm running it off a 12-volt battery. And still, there is like 2.5 amps going into the circuit because there are more losses into the actual wires compared to the simulation. My inductor is especially getting hot because it's handling over 30 amps. Now if I put a piece of iron inside the coil, the current goes even higher. This is because of tons of thermal losses. Ow! Due to huge eddy currents and magnetic losses through the ferromagnetic metal. But low resistance non-ferromagnetic metal won't have as much losses, so the current won't rise as much. If I put my stainless steel plier in the coil, the current rises to 17 amps. And it gets quite warm right away. Ooh. Here, let's put this in. Wow, the power! It works! Let me show you some waveforms. This is the gate voltage of the Mosfet. I don't really like the slow rise time, otherwise it's as expected. And here's the drain voltage of the Mosfet, the half sine wave we talked about at around 26 kHz and 37 volt peak. And this is the magnificent sine wave across the resonance components at 37 volt peak, which means there is around 37 amp peak through my inductor here, which is of course at no load. When there is load, that current will add to it. No wonder it gets so damn hot. Oh, it's burning. I need thicker wire. And there you have it. I made my own induction heater with no protection. This is... Yeah, the circuit works, but it's not a product. It can easily die in a fiery doom. I added an article with more details to my website if you're interested. And last but not the least, listen to music using my sponsor Raycon's earbuds.
It's irrelevant.
That protects my revenue, you dummy. Listen, you can't go wrong with Raycon. Just listen to the sound quality. Well, you can't hear them, but Raycon has a 45-day free return policy. You buy them, you try them, you like them, you keep them, otherwise you return them. What's the risk? Their newest model, the Everyday E25 earbud, is their best one yet. Super small with tons of control without sacrificing the sound quality. You take them out of their box, they turn on and pair to your device. The box itself has batteries that charges your earbuds for up to 24 hours of playtime. You go camping with no chargers, you'll be fine. So don't waste time. Order them from buyraycon.com/electroboom and save 15% and enjoy the sound quality you deserve. And thanks for watching.